Welcome to the 2015 NASA Ames Summer Series. When you watch science fiction movies, you watch vehicles that go into space and return into planets with ease, just like a plane. The reality is, if you re-enter any atmosphere, you need materials that will protect your entry due to the friction that is created by the atmosphere. NASA as an agency is the most experienced in designing and developing re-entry vehicles into atmospheres. And we're currently working on the next vehicle that will take us beyond low Earth orbit. Today's seminar, entitled Burn to Shine, Experience and Lessons from the Orion Heat Shield, will be given by Jeremy Vander. Jeremy has a Bachelor's of Science in Aerospace and Mechanical Engineering from the University of California at Davis. And then he went on to get a Master's in Science and Engineering from the University of California at Davis. After that, he has joined us here at NASA Ames, first as a contractor and now as part of the team. He is currently the Deputy Thermal Protection System Manager for Orion. Please join me in welcoming Jeremy Vander.
All right, thank you very much. Thanks everyone for coming today. As was previously introduced, I'm Jeremy Vander. I'm the Deputy Manager for Orion Thermal Protection Systems. And I wanted to give you a four-part story today. I'm going to give you a little bit of background about Orion, the program, then some overview of the manufacturing experience for the heat shield that we had on the Exploration Flight Test 1, EFT1, that we just flew in December. I'll talk a little bit about that flight test and the post-flight analysis that we've been doing, and then talk about how we're advancing forward into the exploration missions or the EM missions that come beyond that. And the picture there is of me looking at the EFT1 capsule just on the day of recovery, and in the same way that I appear to be looking at awe in that capsule, sometimes I look back at the whole journey to this point with a little bit of awe. So I hope to share that a little bit with you today. So the Orion program and Ames's role. So Orion started, or the program started in 2006. Then it was called the Multi-Purpose Crew Vehicle, or MPCV. At the same time, NASA recognized the need for a TPS Advanced Development Project, or ADP. There's a couple of us with the shirts on in the room today. That ran from 2006 to 2009, and its purpose was to get started early on a large-scale ablative heat shield, technology that NASA had not pursued since the Apollo program ended in the early 70s. That ADP was based here at Ames, and it provided the early development work for the program. In 2009, the Orion contract itself was awarded to Lockheed Martin, who then took on the work. And Ames has continued to support that work with arc-jet testing, thermal and structural analysis, material development, technical leadership, and continues to do that today. So the Orion spacecraft really consists of three parts, three modules. We have a launch abort system, a crew module, and a service module. The launch abort system is only there in the case that during ascent there's a problem with the booster, with the launcher, and it pulls the crew module with the crew off to perform a safe landing while the rocket is unsafely doing something else. Once a nominal ascent happens, though, we end up in our on-orbit configuration. We've got the crew module and the service module together. And you can see those modules here on the right of the chart. Today I'm going to be talking about the heat shield, which is the base of the crew module. So on the way up, it's at the back, but on entry, that's the part that comes in first, and that's the part that really protects the vehicle from the heat of reentry. So if you know any history, even a little bit, you should notice that the Orion architecture, the modules, they look a lot like Apollo did. And so here's a brief comparison of Apollo to Orion. So Orion is larger than Apollo. Apollo was a little over 12 feet diameter, a little over 3 meters. Orion is 5 meters diameter, 16.5 feet. Apollo is designed for 3 astronauts. Orion is designed for 4. But one of the major differences between the two programs is that in the Apollo program, those missions were designed for mission durations 12 to 14 days or so. Orion is being designed for upwards of 200 days in orbit. So even though the sizes may look kind of similarly when placed in scale on paper and you're only one more crew, there's a lot more going on with Orion because of the focus on the long-term mission duration, flexibility to go to destinations and perform missions that are a little bit beyond what the Apollo program did. So before going too much further into heat shields, we need one brief slide tutorial on ablation and atmospheric entry. So it's really a power problem when you come to think of it. Now, one of my colleagues posed it very well that way. So an entering spacecraft, whether it's entering Earth's atmosphere or anywhere else, is doing an energy exchange. You're exchanging kinetic energy or your orbital energy into heat, basically, changing it into heat to slow yourself down. The faster that entry is, the more heat is generated, and the less time you have to dissipate it, either by absorbing it into the vehicle or ejecting it away from the vehicle. Convective heating kind of goes like the cube power of velocity. So as your velocities go up, your heating goes up very, very quickly. Earth entries from low Earth orbit are typically around the 7 kilometers per second range. That's where Space Shuttle would come in from, or other vehicles from low Earth orbit. And today's materials that we have, insulative materials or materials that might be reusable, simply cannot stand the heat energy that results when you enter faster than that 7 kilometers per second. So if you're going to do something like that, you need to get into ablative systems. And so instead of simply insulating a spacecraft from that heat, what ablative systems do is actually consume that heat energy through different chemical processes, vaporization, sublimation, pyrolyzation, et cetera. So one of the other benefits that they have is that when the materials do this, they tend to eject gases out of the vehicle and push the boundary layer up away from the vehicle, sort of pushing the heat away, if you will, to keep the spacecraft cool. What they're really doing, if you think about it in a broader scale, is they're providing power out of the spacecraft during entry. Instead of taking all that energy in and soaking it and through an insulative technique, they're actually ejecting power out. So that's ablation in a nutshell. So let's get into the Orion system specifically. So for the EFT-1 flight test, this is a picture of the heat shield right before the paint went on in the lower left there. It's the largest ablative heat shield ever made on this planet, I like to say. It's made of a material called Avcoat, and a specific formulation of Avcoat called HCG, or honeycomb gund. So what Avcoat is, it's an epoxy Novolac resin that's injected into an open cell fiberglass honeycomb matrix on top of a carrier structure. And so for our size, for Orion, and this is the same system that Apollo used, for our size for Orion, on our 5-meter heat shield, we have over 300,000 individual cells within this honeycomb matrix that were filled. When we were all done, the whole thing weighed about 4,000 pounds, 1,800 kilograms, and about a quarter of that was the Avcoat material itself. And you can see on the right, kind of get a sense of what this looks like zoomed in. The upper picture is of one of our test articles of this configuration. That's what it looks like before entry. You can kind of see the honeycomb structure in there, and then the brownish, purplish ablator in each of those cells. And then after entry, since it is an ablator, you can see the charred surface on the lower right there. And that's the way that the whole heat shield looks after it enters, and we'll talk about that a little bit in a minute. So if you flip this thing over, the back side of the heat shield looks like this. This is the carrier structure, was what we call it. It's a carbon laminate skin. It's got a spider web of titanium stringers on the back. And the reason it looks similar to a bridge is because not only does this heat shield have to protect the spacecraft during entry from entry heat, this is also how we splash down in the ocean, right? The mission for Orion ends with a splashdown into the ocean, and the heat shield is what you land on. So not only are you protecting from entry, you also have this other design constraint. You have to take all of that splashdown load, which is why it looks as beefy as it does. So how do we make this stuff? The answer is exactly the way we did before. So this is a photograph of Apollo heat shield manufacture from the late 1960s. And the way this works is you have your carrier structure built, you come in and you adhere an open cell honeycomb matrix down on that structure, and then fill each individual cell of that matrix with the Avcoat ablative material through what are essentially glorified caulking guns. So this is how Apollo did it. And to get a feel of how we did it, got this little video here. It was playing. So we've got the heat shield sitting on a table there in the back. And there's a crew of technicians that stand around it. In this case, we used a crew of 6 technicians, 2 shifts a day, 6 days a week, and it took about 4.5 months to get this done. And you just sit and gun individual cells. You can see the guns they're using there. They take a cartridge full of the material in the back. They're pressurized and heated, which are the wires hanging down. And you just pick out your section, put your earphones on, and go for it. So you can see this is a hand process. You see fingers involved and all that, and that's the way Apollo did it, and that's the way we did it for EFT1 as well. Let that finish out. So there you go. To kind of give you a sense of the way that this progressed, this is a picture of the EFT1 heat shield, the flight article, sort of about midway or so through manufacturing. And you can kind of see the 3 different stages here. Because the material has we call it an out time, it's a shelf life. So it expires some number of days after it's actually made. You have to use it by that time and cure it by that time, otherwise it becomes bad. Our heat shield is big enough that we can't do the whole thing in one go with one batch of material, so we do it in sections. So we have, on the top there you see a picture of unfilled honeycomb, so that's the honeycomb matrix laid down on the carrier structure. The purpler sections are areas that have just been gunned and have not been cured yet, and then the more tan sections have been cured. So you lay down your honeycomb, gun a section, cure, gun the next section, cure, gun the next section, cure, and move on like that. And then at the end of the day, there's one final cure at a higher temperature to kind of lock the whole thing together, which will become important in just a minute. So we had some challenges on the EFT1 build. We had 2 major issues, and as we'll talk about, neither of them were actually new to this system. The first issue we had is the flight heat shield avcoat cracked during the final cure. So this is the thing we're supposed to fly in a year, comes out of the oven, and it's got cracks in it. Primarily, those cracks occurred in the seams between those honeycomb sections. So the honeycomb goes down in panels. We don't have one big 5-meter disc of honeycomb. It goes down in panels, so there's seams. And that's where our cracks occurred. The second problem we had is that we started to show analytically that the heat shield, the avcoat on the heat shield might crack during the mission, either by getting cold on orbit or due to the stresses of entry itself. This was largely driven by the strengths we were getting from what we call witness panels, which is how we sort of verified workmanship on the flight build. I'm going to dig into those 2 issues here in the next couple of slides. Cracks are not good, right? If you have a crack in your ablator, then you've opened up a pathway for hot entry gases to get down into your structure, which is the very thing that you have the heat shield for in the first place, is not to allow that to happen. So let's talk about the first problem first, manufacturing cracks. So we pulled the heat shield out of the oven for its final cure, and we found 28 cracks in various locations on the heat shield, and you see the map of those cracks there on the lower left. We think those were likely caused by thermal expansion, by stress concentrations at the seams, and I'd also add probably some material quality problems along those seams. And you can get a sense for what they look like. We're not talking about vast canyons here. We're talking about little fractures there on the right, if you can see them at that resolution. Yeah, you can kind of get a feel for it. So, needless to say, there was consternation and gnashing of teeth because of this. But we got through it. How did we do that? Well, we fixed them, right? One of the things that we got by using a system that had been done in Apollo was a whole set of specifications for how to fix problems. So they actually had repairs for this type of issue already spec'd out to use. And we implemented those repairs. Now, because things were a little bit different and because you always check somebody else's work, we went ahead and certified those repairs for our own flight in our own way. The way we did that is, you've got on the upper right there what a crack on the heat shield will actually look like. On the lower right, you've got that same crack has been repaired with these overlapping plugs. On the side, what we did is we built up test articles with the repairs in them, in this case, ArcJet test articles, with overlapping plug repairs. We tested them in the ArcJets, took them out, checked how they worked, checked all the temperature data, and they were all fine. So we certified the repairs for flight as well as the pristine system. So I mentioned that we got some of these spec repairs from Apollo. When this happened, one of the things we did is we actually commissioned different folks around the country to go and photo survey whatever crew modules we could get to in the various museums. And it turns out they're basically all there to go look at and photo survey. So we did that. And these kinds of repairs are on every single Apollo crew module that you can go look at. They're all there, lots of them. So repairs of this nature are a standard part of the honeycomb gunned avcoat system as evidenced by the Apollo capsules. Didn't make us feel better at that time, but it is something worth noting. And we're going to talk a little bit about that too. So the second problem we had was we were actually predicting that the ablator could crack, or we call it negative stress margins, during the EFT-1 flight. But it was impossible to verify whether or not that was true on the full flight article, right? If you think about a 5-meter heat shield sitting there that you've basically built in situ or in place, put your honeycomb down, gunned it, and it's done. We don't have a way to test that, to bend it, pull on it, heat it up, cool it down in the same way that we expect to happen during the flight itself. So we have to rely on side methods or coupon bench level tests to do that. The way we did this on the flight build is we used something called a witness panel. A witness panel is a panel that sits off on the side. You can see it here on the left in the green circle. Where have I lost it? There it is. The green circle here on the left. So you'd have the technicians gunning the ablator into the heat shield. After some time, they'd turn and gun some into the witness panel. Then they'd turn back to the heat shield, then back to the witness panel, back to the heat shield. And so the idea is that this witness panel on the side is representative of what's being done on the flight article. So we take that witness panel, cure it, cut it up, and start testing it. We did pull tests like you see in the upper right there, tension tests. Measure the strength, measure the density, et cetera. And the thing that happened is all of that data was coming back with lower strength primarily and density than what we expected or what was even required. The plot on the lower right is showing the region that would be good or in spec is sort of this middle upper square here. And then I plotted the data points from those witness panels. You can see there's a large portion that are out of that box. So when you go and fold those kind of results into the flight predictions into the predictions for the flight test, that's where we started seeing the negative margins come up. So that left the hanging questions, well, are these witness panels faithful witnesses, right? Are they actually what's on there? But that's what we had to deal with. That's what we had to work with. So it turns out that Apollo fought through this as well. They had negative stress predictions for their flights. So these are excerpts from the final thermodynamics reports from the Apollo program in the late 60s. You can see the highlighted area on the top, structural analysis, predict that cracking of the blader may occur. Wow. And then on the bottom, so what did they do about it, right? They went and decided and found are cracks okay? And they did, right? Cracks predicted for the crew compartment will not produce structural overheating. So we think it might crack, but it's okay if it does. And so we went down that same path. We built test articles with cracks, in this case another ArcJet test article with a crack, tested them, measured how they performed, looked at all the data and said, you know what, yeah, Apollo, we're coming to the same conclusions that they did. If these cracks form, we'll be okay for the EFT-1 flight. So I've talked a bit about the problems on EFT-1. We've shown that Apollo had a lot of the similar problems. So this is the first little anecdote that I've come up with here based on this experience. Siren Song of Heritage. So Orion selected the Avcoat heat shield, the honeycomb gun Avcoat heat shield, primarily on a heritage argument. And I'll quote myself on the engineering definition of heritage. So it's a previous system that has been designed, fabricated, and operated very, very similarly to a proposed system. So something that's been done in the past that I'm going to do the same way in the future. And programs like this, organizations like this, right? Heritage systems make us feel good because it's been done before, so we can do it too. The problem is that heritage systems come with heritage policy and somebody else's risk appetite. What I mean by that is the program that implemented a certain solution in the past, you may build the same thing, but you may not have the same design rules that they did, or you may not be able to handle the same level of risk that they did. So Orion, we recognize the value of having a heritage system, but we didn't quite count the cost of the challenges that Apollo saw and that we found sort of in retrospect going through all this. Apollo documentation shows that they had cracks in their fabricated heat shields, particularly early on. On the Orion program, we went straight to the first full-scale article was the first article we were going to fly. That was the EFT-1 heat shield. Everything else to date was, up to that point, was small. So as Apollo built large-scale things, found cracks, worked around them, got them sorted out, and then went on to the flight articles, we went straight to the end because it was a heritage system, right? On the stress analysis side of the house, Apollo used some design policies that Orion has not allowed itself to use, frankly. And I'll talk about that a little bit in the past too. And that kind of got us into the pickle we were in with the negative margins and having to show cracks good in the same way that they did. But needless to say, the EFT-1 flight test was a success. So let's section to part 2 of the story, or 3 if you count the overview. So exploration flight test 1, December 5th, 2014, 2 orbits around the Earth, about a 4-hour duration. First orbit, very low orbit, Second orbit kicks out to almost 6,000 kilometers. So to give you a sense of things, the International Space Station orbits at about 400 kilometers. So we're out at 6. The moon's at 384,000 kilometers, so we're not quite there. But we're quite higher than the typical low Earth orbits that you see. The reason we did this was to test one of the main reasons we did this was to test the thermal protection system, to test the heat shield. So we entered at about pushing 9 kilometers a second. Entries from LEO are about 7 kilometers per second. Entries from the moon may go a little north of 11 kilometers per second. Okay? So, and then the motivation for the title. So this is a video of the Orion capsule entering, taken from a DoD asset during the EFT-1 mission. So you've got the capsule there in the upper left.
We're tracked. Copy.
Acquire at Mach 22, 160,000 feet. We actually get good infrared imagery, and you can start to see features come out in the infrared because they're heating up at different temperatures because they're made of different materials. Those are the compression pads, or where the service module and the crew module are integrated together.
Left wing down, okay.
And then we come down and splash down very nicely into the Pacific. We're about 200 miles west of the Baja Peninsula for this. So one of the important things about EFT-1, I mean, remember, this is the first ablative heat shield of this size that anybody's ever built, and certainly the first one that NASA's built in a long time, is we worked very closely with the recovery operations to make sure that the vehicle we got back was as pristine as possible so that we could do post-flight inspections, get all of our data off of it. For EFT-1, the U.S. Navy accomplished this recovery, Mobile Diving and Salvage Unit 11-7. So I worked with them very closely to talk about what parts of the vehicles are very important. Please don't touch them. Please don't touch these parts because it'll hurt you. You can touch these parts because they're not as interesting, all of that kind of thing. And they did a great job. We recovered onto the USS Anchorage, which is a landing assault ship that the Navy has. And you can kind of get a feel for how this worked from the picture in the lower right. These ships have a giant garage door, as it were, on the back. They can ballast down, flood an interior volume, and you can float things in and out, and then ballast the ship back up to pick up what you've recovered. And that's what we did. Floated the vehicle in, and then ballasted the ship up underneath it. And the heat shield did great. So this is one of the first images we got once it came back from a diver in the water before anyone else touched it. And we've got photo surveys that have happened almost at every point now since before flight to in the water to on the ship to back at KSC and so on and so on. So we can compare what's happened to it to make sure anything we see is because of the flight and not because of somebody dropped a hammer on it afterwards or someone nudged it or from recovery damage and all that. So we've been very careful about delineating all of that. So here's what the heat shield looked like after the flight. Once we got it back, took it off the vehicle. This is down at Marshall Space Flight Center where we did our post-flight sample extractions. So there's a couple interesting features to point out. The stagnation point there, or the point where the air theoretically comes to a stop as the vehicle enters, is over on the right. It's offset from the center because we have a lifting entry. So the vehicle comes in with an angle of attack. It's a lifting body. And so all the streamlines emanate from that point. You can see features like transition wakes here. So this is where the flow would start laminar and then get turbulent because of some protuberance or because of the Reynolds number getting high enough or what have you. In this case, protuberances, right, because we have wedges. We have damage from the recovery process here that we see. And then you can see our repair plugs. These lines of the white circles are all the repairs we made to those cracks that we talked about before. So what we've done is, we're in the midst of an extensive post-flight evaluation. And so a team from here, from NASA Ames, went down to Marshall Space Flight Center, worked with the crews there. And the reason we were at Marshall is because they have an extremely large 7-axis milling machine. And so what we did is we identified squares or islands of material that we wanted to take samples of. And the Marshall guys were able to set up their machine to progressively machine down the surface of the ablator to leave these islands of samples for us then to come off at the end and just take off with a hand tool. It worked out really well. It also worked out well because they were going to machine the Avcode off anyway. One of the things that the program is doing is actually reusing the carrier structure from the EFT-1 flight test in water drop tests for development purposes up at Langley starting in the late fall, I think. So the AVCO was coming off anyway, so we got as much of it as we could. So we took 192 samples of these squares. They're all here at Ames now. We took over 200 recession measurements, or a measurement of how much material ablated away during the entry. And these are getting characterized and cataloged and everything here now, and then they're going to ship off in batches to various places across the country for further analysis, mechanical properties, thermal testing, what have you. And that'll go on for a while. So the flood of papers is just beginning. I can feel it. Okay, so moving forward a bit to exploration mission design. That's what we're in right now. So the next steps in the program are 2 flight tests, exploration missions 1 and 2. Exploration mission 1, or EM1, is set to go off in 2018 or so. Right now it's being characterized as a distant retrograde orbit, or a DRO. And this is an orbit that actually takes apogee out past where the moon is, so past 380,000 kilometers or so. There's a couple reasons for doing this. One is to demonstrate heat shield capability at entry speeds that are up around 11 kilometers per second. There's test objectives about radiation protection that far away from Earth. And you get to say that it's the furthest out that any human-capable spacecraft has ever been from Earth. So that's nice. Then we have EM2, which will be the first crewed mission of Orion, which is set around the 2021 timeframe. And that'll be, you can think of it as a refly of Apollo 8. So it's to the moon, orbits around the moon, and back. All right, and that'll demonstrate crewed operations. So we have these 2 missions coming up. We just had a flight test. We built a heat shield a particular way, and we're going to change it. So you may have noticed, seen some of the media come out back in November about changes to the heat shield architecture, changes to the way that the AVCO is put on. So why would we do this? Let's talk about it. So motivations for a new architecture, in this case, and I'll outline it a little bit, blocks of AVCO instead of this honeycomb gun system. There's 2 main motivations. One is technical. We talked a little bit about the challenges we had with the EFT1 build. Can we improve the manufacturing enough? Not have cracks during cure? Can we improve the material strength enough so that we're not predicting these negative margins all the time? The EM flight loads are higher than the EFT1 flight loads, so we have more of a challenge to go there. The second motivation is programmatic, particularly schedule. So fitting the honeycomb gunned architecture into the program's schedule box has proved problematic. And a lot of that is because the honeycomb gunned manufacturing process is serial. So you build your carrier structure, you put your honeycomb down, then you gun all the ablator in, and then you cure. And you can't do one step before the other or in parallel with the other. They have to go serially because of the way that it works. If you came up with a system where you could build things in parallel, you would save time. So the thought is, what if we made blocks of this AVCO ablator? Don't put it in a honeycomb. We can make those in parallel with the carrier structure. We have to install those blocks, but that'll take less time than it does to install the AVCO on a honeycomb gun system, so we'll save time and fit ourselves back into the schedule box we've been given from the agency and at the end of the day from Congress, right? So what is this architecture? So we're not changing the ablator, right? It's still AVCO, the same formulation of the ablator. But instead of gunning it into individual honeycomb cells on a carrier structure, we're molding it into blocks to do that in parallel with the carrier structure. Same ablator, molded into blocks instead of gunned into a honeycomb. And then in between those blocks, we're putting RTV, or room temperature vulcanizing adhesive, in between. So you can see how this might play out on the Orion heat shield on the lower left, about 300 or so of these blocks. And there's some precedent for this in the past, right? Tiled systems have flown, certainly. SpaceX is flying an ablative tiled system right now. We already talked about heritage and the problems with that. Is that system sufficient heritage to say this one will work? Time will tell, right? So what are some of the advantages and disadvantages? Well, advantages of a block system, and particularly this one, is that you've got what we'd call true acceptance testing and verification of the ablator before you commit to putting it on the carrier structure. So remember with the honeycomb gun, with the EFT1 heat shield, the honeycomb gun architecture, we had these witness panels that we had to presume were faithful representatives of what was actually on the flight vehicle. With a tiled system, you can make your flight tiles or your flight blocks, pull on them, test them, make sure that they're good before you actually put them down, right? So you know what you've got. That's one advantage. Parallel manufacturing we talked about. Cheaper fabrication costs because of the reduction in labor time is a motivator. Faster test article production throughput. again, because you're molding things instead of gunning things individually into cells. We've actually found that the molded ablator is stronger than the honeycomb system. You can, in some ways, the honeycomb matrix actually is introducing little stress concentrations into an otherwise homogeneous material. And there's less density variations. You can control things at the molded block level as opposed to each gunner's hand that day or week into each individual cell. There are disadvantages. We've introduced a new system element, right? So now not only do we have the ablator itself, we have these seams between blocks, an often overlooked portion, but a very important portion. So we have to go characterize that. Will these seams work? Will they hold the blocks together? Will they ablate properly? The blocks have a less capable attachment system than that honeycomb architecture. They're less tolerant to first failure modes, and I'll go into that a little bit more. What I mean by that is, while the blocks may be stronger than the honeycomb gun system, when they do fail, they tend to fail more energetically, shall we say, than the cracks we saw on the honeycomb gun system. Then we also have to deal with the differential recession between the blocks and the interfaces that we've laid out. So let's dig into two of those challenges in particular. So the first one, this differential recession problem. Anywhere you have two different materials on an ablative system, they're going to recede and ablate at their own rate, right? So one of the worries we have is that these seams between the avcoat blocks will actually start to protrude or gap below the surrounding avcoat, causing local heating augmentation, right? If you stick something up into the flow, into the airflow during entry, it's going to cause local heating augmentation. If it does, it means you need more avcoat thickness behind your the thing that's augmenting the heating, which means your mass goes up, and you can kind of get into a little bit of a runaway thing with that. So one of the ways we look at this is through progressive arc jet testing here. So up on the upper top, you've got a simulation of the EM entry profile. It's actually a skipping entry, so you've got two spikes of heating that occur. And what we've done is we took 4 separate test articles. This is a Pathfinder. We took 4 separate test articles, all built exactly the same with this RTV seam in the middle. Run the first one through the first part of the trajectory, take it out, measure. Run the second one through a little bit more of the trajectory, take it out, measure, so on and so forth, to get a sense of how this interface might perform over the time of that trajectory. And so you can see we start to form a little bit of a fence there at the end. So this is the Pathfinder, first time we did this. We're just getting into this now, actually running currently in the ArcJets with a whole series of different kind of profiles correlating to different kinds of trajectories, different places on the heat shield to get a sense of how this works. We're also, as an aside, implementing a system that'll let us measure that differential recession real-time in test instead of having to test different articles for different lengths of profile testing, because that can get quite expensive. Another challenge with this system, and it's kind of a challenge in general, it's more of a design philosophy thing, it's a risk posture kind of question. Likelihood and consequence of failure. So on any system, right, the consequence of a failure ought to, or should, dictate what your design policy is for that system. We talked a little bit about Apollo. They designed to average material properties, right? They showed that, well, it might crack, but if it does, it's okay. So what you might call that is, if you're talking about the failure of a crack, you have a fairly high likelihood that will happen, but the consequence is low, right? It might happen, but if it does, it's all right. What we found with the blocks is, as I've already mentioned, the likelihood of a failure happening, of a crack happening, is much lower. But if it does, it's a lot worse, or we expect it to be a lot worse, right? So you have a high consequence system, which must have a very, very, very low likelihood of that initial failure occurring. And you approach these two problems in very different ways, right? If you've got a bucket, a population, if you will, of strength data per se, like the plot in the upper right, and you lay it all out, let's say it's a nice, pretty Gaussian that comes right out of a textbook. You can design to the average of those properties, like Apollo did. And that's not very hard to do, right? You just look at your data, you take the average, you design to that, and if your system closes, you say, great, because I know that if it does fail, if I get some material on the vehicle that has less strength than that, I know it's not that big a deal. Well, it takes a lot of time and effort and sweat to show that it's not that big a deal, right? And you can think of that if you're familiar with a 5x5 risk chart, or some people call it a temperature chart. If you're going to move a risk from the right to the left, so decreasing what you think the consequence will be, that takes a lot of proof, right? You have to show that that's actually the case. So if you're going to kind of take the first road easily and allow something to happen, it takes a lot of work to go then and show that it's okay if it does, right? This is fracture tolerance or defect tolerance. It's a lot of work. If you flip it around the other way, where we are with the blocks, if either your design policy simply won't let you design to mean our average properties, which is the case on Orion, we use more, I don't know, I wouldn't call them advanced, they're just different policies, designed to A basis, B basis properties. So we have to design to the 99th percentile low strength of our population, or 95th percentile low in the case of B. You're coming at the problem a different way. You're investing your time and money and sweat up front to show that your design closes to a very conservative estimate of what your strength is, right? So you say, I've got this body of data, population of data about strength of the ablator in this case. I'm only going to pretend that I'm going to get the 1 percentile worst case of all that data, and I got to make my design close to that. And that's where you spend your blood, sweat, and tears, as it were, right? That costs a lot to get the design that tight, because you're saying that I'm not willing to go down the path of showing that this failure is okay, because I don't think it is in the first place, and second, because I think it'll cost too much time, effort, and money. So in that case, if you want to think of it as a 5x5 again, you're spending your dollars, your time, to drop the likelihood down, or to show that the likelihood of your failure is way down here at the bottom. Now, I picked this chart for a reason, because where do those two triangles end up in terms of a qualitative risk? The same place, right? On this particular scoring chart. Different programs have different charts that score these differently. They could both be called high-risk systems, but they're very different in the way that they operate, right? Okay, so my second cutesy notation, right? The dragon behind the smoke. So knowledge of a mature system versus the uncertainty of a promising new idea, right? So Orion, we built, had challenges with, but still flew successfully the EFT1 heat shield, right? But it was enough of a technical challenge, there were enough program challenges that's motivated a change. So we had this challenge we knew, the dragon we knew, right? We don't want to fight that dragon. We want to give me a different dragon. Well, we've got this other one that we think might be good, but it's kind of clouded by immature design, right? We're not sure what we're going to get into yet. And when you first start out, that's always the case, right? A proposed system is always less known than a known system, right? It's obvious. And when you start to kind of brush away the smoke, you might find a different dragon than the one you initially thought you had, right? I'm not saying Orion is here, but this is something to keep in mind, as it were. Consider it a lesson, right? You can never bank on a proposed future system being exactly what it's sold to be. One of the other things that I feel like is important to point out that it's really driven home is this idea of separating technical and programmatic constraints, right? It's kind of like trying to get to Neverland, because they're always coupled, right? In the case of Orion, changing the heat shield architecture after a successful flight test is really trading one set of technical challenges for another set of technical challenges in pursuit of a programmatic advantage, right? I mean, that's kind of the end of the day where we are. Orion, the program, is looking for a workable balance at that program level. Workable balance does not equal optimal in any one sort of evaluation metric. It's not going to be the perfect technical solution. It's not going to be the perfect programmatic solution. It's a workable balance. And that's what projects try and do. Each organization and the sub-teams within each organization is going to weight different metrics differently. The program wants to be sort of technically good enough or technically responsive to what it's been asked to do within the budget and cost constraints it's been given. What's every other hearing on Capitol Hill about? Why are you costing so much? Why are you taking so much time, right? If there's a contract involved or a contractor involved, all of those program desires have to be translated into contract language, and that's what the contractor has to deliver on. So the contractor does whatever's in their contract, right? It's difficult to get a large contractor to exceed requirements, right? Because that costs more money, which is what the program was trying to do in the first place, is not spend that money. You've got engineering communities who, if they're trying to decouple this technical programmatic thing, will be proposing the best technical solution irregardless of the cost, right? Best technical solution no matter what it takes. I would love the best technical solution. Everybody would love the best technical solution, right? It's a matter of fitting that into the box you've been given as a program to operate with in both time and money. And as always, whenever you've got challenges, there's the whatever my idea is the best idea, right? And that's out there too. So all these things kind of balance, and it's been quite interesting to see how these have played out through the Orion experience to get to where we are today. So despite substantial challenges, right, Orion flew EFT-1 very successfully. Those flight test objectives were satisfied, almost in total. The evaluations we're doing now of that vehicle, particularly the heat shield, are going to be the first publicly available data set on a human-capable ablative system since Apollo. Okay? So there's other crewed ablative systems flying now, commercial crewed systems, et cetera. Those data sets are not nearly as extensive, and they are not going to be publicly available. This will be the first one since Apollo, and it is going to be an exciting data set. Already kind of seeing and being a part of developing it, it's going to be tremendous. Set out your PhD thesis plans now. The other thing, to kind of leave with is every engineering effort is very coupled, right? You have the technical, you have the programmatic, and you have the risk. And none of these things can be treated separately, right? You may attack them with separate groups or whatever, but at some point they all have to come together. What works for one program may not work for another program, and in any of these things, right? A technical solution of one program may be great, it may not work in the programmatic constraints of another, or in the risk appetite or posture of another. And it's very interesting to observe how all these things interplay and how all these organizations interplay, and has been interesting on Orion. So that picture of Earth there is taken during the EFT-1 mission. I always like to point out it's quite a bit smaller than what you see on NASA TV going by under the space station. So it's an exciting time. I think that we're going to have a great path forward on Orion. I'm excited to see where it goes. So thank you very much.
So now we would like to take some questions. Please make a file in the microphone in the center aisle and ask one question. Keep it short and succinct, please.
One quick thing about the design of the Avcoat honeycomb versus the new block heat shield. Something that wasn't mentioned in the talk was an issue with when you're injecting it into the honeycombs, the occurrence of voids, little gaps and bubbles inside those individual honeycombs. And is that addressed in the new block form design?
Yeah, so what Jeff is getting at is when these gunners inject the Avcoat in the honeycomb, what we've seen can happen and found some instances on the flight build for EFT-1 is that you get these voids within a cell, as it were. On EFT-1, we attempted to screen those out with X-ray. So we used backscatter X-ray across the entire flight build, and we're trying to discern where these voids were. Problem was we didn't have a solid reference case, right, for the X-rays, because we've got the carrier structure behind it. So they're kind of difficult to find. So you're kind of eyeballing where on an X-ray image things might not look quite right. With the blocks, what we're going is to get, first of all, we've seen less occurrence of the voids. I don't think we've actually seen any voids so far in the manufacturing. But we're also going down the path of X-raying those blocks separately on a table, and we're probably going to end up CT scanning them as well. So I don't think the voids will be more readily addressed in that system. Does that get what you wanted?
So while we're waiting for the next question, I'd like to switch places with you.
Okay.
I have a question about the best technical solution. Would you recommend for future missions, is it possible for commercial industry to find these, or do you recommend the path that NASA has developed through the space heritage, and maybe can expand on that topic?
Sure, yeah. Yeah, I think it's definitely possible that the commercial programs could find solutions, that would enable other missions. Is that kind of what you're getting at? Yeah, that would enable other missions. That's not what they're required to do right now, right? Their contracts are for space station resupply and crew rotation. So that's what they're working to. And those are the solutions that they've selected are to answer those missions within their cost and schedule boxes, right, that they've been given. There's nothing, I guess the way I'd say it is, within the way that the commercial crew programs have been set up, they get a lot of help from NASA. NASA provides a lot of expertise, particularly in the TPS area. So in the same way that expertise has been given to them to do the mission they've been asked to do, if they were to set out and do an exploration mission, a more capable heat shield or something like that, they'd receive that same help, and they could probably go do it.
So with the tiled solution, is the material in the seams necessarily expected to also be ablative, or is it merely must it be ablated for the system to work? Or I saw I mean, we had the demonstrations, but must those joints also, is that required as part of the whole heat transfer of the system?
Pretty much yes. Yeah, so if in the hypothetical case where you had seams between blocks that didn't ablate at all, then whatever heat got into those would conduct directly down to the structure instead of being consumed through the ablation process. So you'd call that a thermal short, as it were. But then also, because we want to keep the surface as smooth as possible so that we don't have local heating augmentations, if one part's ablating, you kind of want the whole thing to be that way so that you kind of keep the OML, the outer mode line, as smooth as you can.
Jeremy, thank you very much. That was an outstanding talk. I'd like to know how much extra mass margin you think is on the heat shield because of our inability to exactly predict, model, simulate, and ground test the thermal and structural loads on the system. How much could we take off if we had a perfect predictive capability?
I'll be able to answer better when we're done with the EFT1 post-flight analysis. You know, to eyeball it, just based on the margin policy we have, anywhere from 25 to 50% in thickness for a lot of different reasons, but probably in that ballpark.
If there are no, we have another additional
Yeah, please.
question?
I was just curious if you could give like a specific example on how to like mitigate the technical risk of the new tile system, like just a specific example, rather than just saying it costs time, money, and sweat.
Sure. Yeah, I mean, the biggest, well, one of the top two issues we have with the tiled system is to verify that when those blocks are bonded to that carrier structure, that they do not come off, right? Because if a block comes off in flight, you're going to lose that vehicle. So that's probably our biggest challenge. So some examples of how we're getting around that is working up all the process controls that are going to be needed to adhere these blocks down. We're doing a lot of sort of benchtop level bending tests, cold soak tests of these blocks bonded down to the carrier, bonded to each other, and making sure that we can test them well beyond the mechanical deflections or the temperature loads that we expect them to see in flight, because they can't come off. Yeah.
So you mentioned different speeds of reentry. I think one was 9 kilometers, one was 11. As we theoretically venture further out into space and return, does that speed go up exponentially? And if so, do we need to sort of build thicker or different shields, or is there sort of a constant speed that is reached kind of the further out you go and come back and things like that?
It keeps going up, right? So the speed you return is related to the speed of your orbital velocity, which is related to the apogee away from the body you're orbiting. So low Earth orbit 7 kilometers a second, the Moon 11 kilometers per second, Mars 13 kilometers a second, and after that I don't know how to quote the numbers, but it keeps going up. Yeah.
So, if there are no other questions, then please have additional conversations in the reception. And we'd like to please thank our speaker one more time.